Electric field can be kind of confusing. It's a theory invented to explain why charges can push each other around when they don't touch each other. The first step of that pushing around is to understand electric fields. Any object that's charged is surrounded by this invisible electric field. We picture the electric field by imagining the direction a positive one would get pushed or pulled. Way back when they were inventing electric field, they didn't really understand the model of the atom, so they literally thought of it as an imaginary positive. If we look at the positive charge, an imaginary positive would always get repelled away from it. So a positive charge would get repelled upward if it were here, would get pushed downward if it were over here, pushed to the right if it was there, pushed to the left if it was there. No matter where we imagine a positive, if it's close to another positive, the electric field lines are always going to point away. If we have the opposite kind of charge though, if we have a negative, an imaginary positive would always get attracted towards it. No matter where we imagine a positive in the neighborhood of a negative, that imaginary positive would always get attracted towards the negative. So we say that electric field always points towards a negative. We have an equation for electric field. It's up here. Electric field is related to the magnitude of the charge. We notate charge with the short form Q. It's going to be in the units of coulombs and divided by r squared, where r is the distance away from the charge. That'll be in meters. K is a constant. It's kind of like pi or the speed of light or other physics constants. If we're in air or a vacuum, the value of this K is a big number. 9 times 10 to the 9 newtons meters squared per coulomb squared. It's a big number, which really what that means is if we had 1 full coulomb of charge, that's going to create a really strong electric field. Usually we'll be dealing with microcoulombs or millicoulombs of charge. Suppose we have a positive 5 microcoulomb west of a negative 20 microcoulomb, and I'm curious about the electric field north of the positive 5. So just to make sense of this, I'm going to draw it out first, and then we'll do some math on it. We've got a positive 5 in microcoulombs. Over here we've got a negative 20, also in microcoulombs, and I'm curious about what's happening north of the positive 5. So I'm curious about what's happening up here. What's the electric field up here? Maybe I've got these two charges, I'm doing a lab and they can't move, so I'm doing a lab at that point. I'm curious what the effect of those two charges at that point is. The distances are given. These two are 12 centimeters apart, and this distance is 9. I'm going to have to flip pages to make room for this, but a couple things jump out at me. I'm asked for electric field. I know that electric field follows that kind of simple equation, E equals KQ over R squared. Since I'm asked to find the electric field created by two charges, I'm going to have to use the equation twice. Once for the 5 microcoulomb and then once for the negative 20. Once I get those two answers, I'll have to add them. But electric field is a vector, so once I get those, I will have to add those as vectors. We'll do the math, we'll flip back and forth and we'll do the math, and then we'll figure out how we're going to add them. If we look at this triangle, the R value for the negative 20 is this big value. We're going to have to do a little Pythagorean theorem to get that, or if you're really on your toes, that's a 3, 4, 5 triangle, and the hypotenuse that we need is 15 centimeters. So double check with Pythagorean theorem. Is always the direction that an imaginary positive would get pushed. So we've already decided that the electric field, because of the plus 5, is going to repel it away, so the imaginary positive would go upward. The electric field, because of the negative 20, a positive would get pulled towards it. So the electric field, because of the negative 20, is actually pulling it down towards the 20. We need to add those two vectors. To add them, we're going to need the direction of that 8 million number. Again, if we look at our 3, 4, 5 triangle and do a little bit of a trig or a little bit of a SOHCAHTOA, the angle up here, I'll let you verify, but the angle up here ends up being 53 degrees. So we've got 5, oops, let's switch screens again. Electric field is, oops, a little bit messy, equal to KQ over R squared. The K is 9 times 10 to the 9. It always is, unless for some reason I switch it so we're not in air anymore. The Q is 5 times 10 to the negative 6. That's what a microcoulomb is. The R value for that one was 9 centimeters, but I've got to put that in meters. And I have to square all that. When you do the math on that, I'll let you verify it. Watch how you use your scientific notation button. But we get a number around 5.55 million, or times 10 to the 6. It's got the funny units of newtons per coulomb. If you think back to the picture, electric field was always a direction the imaginary positive got pushed or pulled. We just figured out that the value of the electric field is this 5.55 number. If we imagine a positive at that 9 centimeter position, the positive would be repelled away from this positive. So this is a vector that's actually pointing straight north. We'll need that eventually to add on to the other vector. The other electric field, due to the negative 20, we're going to do the same basic math just with different numbers. E equals KQ over R squared. That's supposed to be a square. The K is always 9 times 10 to the 9. The Q in this case is 20 times 10 to the negative 6. I don't really care about the sign because I can use my brain to figure out the direction. But I need to take a minute to figure out the R. So let's flip back to the last one. Recognize it's a 3, 4, 5 triangle, but the point 15, the 15 centimeters goes down here, and it has to be squared. When you crunch out the math on that, we get 8 million. So 8 times 10 to the 6. It's in newtons per coulomb. When we do the direction on that one, let's flip back again. We've got 5 million, 5.55 million pointed straight north, and then we've got this 8 million number pointed downhill on a 53 degree angle. It's a little bit weird, but it shouldn't throw us off too much. I've been doing that since really our first day of physics. You draw one. This is our 5.55 number. It was pointing straight north. Where it ends, you draw the next vector. This is our 8 million number. I'm not sure if my scaling's right, but I'm going to put it that long. That's my 8 million. And my SOHCAHTOA told me that this was 53 degrees. We need to solve that triangle, the vector sum, so the very, very start connected to the very, very end, that's the total electric field. That's what we're trying to find. I'll let you verify the math. I think I can squish it in here, but this is classic cosine law. So the E total squared is my 5.55 number squared plus 8 squared, oops, those are squares, minus 2 times 5.55 times 8 times the cosine of the angle between them. In that case, it was 53. So a little bit messy. You got a little bit of work to clean that up, but after doing all the math and square rooting, we get that the value of that number is 6.43. I was a little bit lazy. I wasn't writing the millions, but that's 6.43 million. So that's also times 10 to the 6 newtons per coulomb. After that, you can do a little bit of sine law work to figure out the angle. Always get the angle closest to where we started drawing our vectors. So I would get this angle. Let's call that x. I'm going to squish that in as well. Sorry, it's getting a little bit messy. The sine of x over 8 is equal to the sine of 53 over that number we just found, 6.43. If you do the math on that, you get that the angle is approximately 83 degrees. So my diagram's not quite to scale. That black line, that E total would actually pointing north 83 degrees east. If I write that all that out nice and neat, it's a little bit messy, but hopefully you followed the math of it. The value of the electric field is 6.43 million. Its units are newtons per coulomb. After doing the trig, the angle is 83 degrees, and that was rotated away from straight north. So north 83 degrees towards the east. Outside of the math, what we did here is to find the electric field because of two charges. We used the electric field equation twice and then added them as vectors.